Okay, should be recording now. Um, so today we have Daniel Seita presenting. He's presenting his work. Daniel's a PhD student at UC Berkeley, advised by Ken Goldberg, and he's going to be presenting on manipulating deformable objects using transformer networks as well as model-free and model-based methods. So please, Daniel, feel free to kick it off.
All right, thank you for the introduction. So yeah, I'm Daniel, and it's a great honor to be here presenting at Toronto. So I'll be presenting deformable object manipulation, and this is in collaboration with researchers from Berkeley, Honda, and Google. Yeah, this is what's gonna come. So first, we'll have some introduction, motivation, and prior work. And then we'll discuss 3 research papers that I wrote over the last year that have to do with deformable object manipulation, each proposing a specific technique for doing so. And then we'll end with some ideas for future work and collaboration. So first, why deformable object manipulation? I find it very exciting because if we can get robots to manipulate the deformable at the level of a human, then this would enable applications of robotics in automated sewing and doing laundry, bed making, wrapping, and other applications. But in contrast to rigid objects, manipulation of deformable has some extra challenges. And 2 that I like to identify are as follows. Number 1, it's very difficult to represent the state of an object or the configuration. And that's a very fundamental question that we often deal in robotics for both the robot and the object. Where is it? So if you have a rigid object, for example, usually knowing the pose or the position and orientation is sufficient to characterize the object. But if you have a deformable like the Canadian flag here, if we know the pose of part of the flag, we might not know what the rest of the flag looks like. Number 2, considering this challenge, it's very difficult to design a policy on top of this because of complex dynamics and physics, because if we have a deformable and we perform an action on it, how do we characterize what's the resulting state? So in this talk, we'll discuss some ways to potentially address the challenges using learning-based techniques for robotics. So there's been a lot of prior work in manipulating deformable, such as applications in tying and untying knots, folding towels and laundry, smoothing slightly wrinkled fabrics. What I want to highlight in some of these prior works, especially for the fabrics, is that in the early days, a lot of researchers would use some traditional vision-based algorithm to figure out what is the state of the fabric. And then we can define a geometric controller on top of that, like maybe grip the lowest hanging corner. But over the last few years, the robotics community has experienced part of the deep learning revolution, where we start training policies end to end through a deep neural network. And as a first step in this process, I collaborated on a paper that we presented in 2019 on robot bed making, where we had a blanket and we took an image of it, passed it through a network to figure out where the corner was, and then we could do a corner pulling policy on top of that. So that work served as a sort of a good prologue for what's to come in the next few papers. So in this first paper, I'd like to discuss a way of manipulating deformable using model-free deep imitation learning method. Okay, so here's the context, the problem statement. The goal is to flatten fabrics from highly rumpled, highly wrinkled initial configuration. So here you see some examples arranged by difficulty tier in rows of fabrics that the robot had to smooth. Now, when for doing this project, what we wanted to do was take a data-driven approach and learn policies in simulation. So for this, we developed our own custom fabric simulator for this work. So there's some other fabric simulators out there, such as those from PyBullet, Joko, and so forth. But the issue was that when we tried some of these simulators, they either weren't the right fit for our need, or they were under development concurrently. So for example, with ArcSim and other simulators that the computer graphics community has developed, they tend to err on the side of being very high fidelity, but also at the cost of being very slow. And so what we needed was a simulator that was reasonably accurate, or just accurate enough, but which was also fast enough for us to get a lot of data. So that led us to develop this simulator where we have fabric as a 25 by 25 grid of vertices, and that's the underlying state. And then we can get an observation by taking a top-down image using Blender. And from this, the goal is to maximize the coverage over that, the background plane. So when doing that, the robot had to take action. So how do we define an action? We define the action using a very straightforward pick and place action, where each action is 4 numbers, 2 to represent the picking point and 2 to represent the placing point, or otherwise the pull vector. So we use a fixed height delta. So the robot will pick at a point, lift it up by a specific height, drag it across the plane at that height until the placing spot is reached. So with this context, we then use deep imitation learning to train fabric smoothing policies in simulation using Dagger. So just to quickly recap, Dagger is a very popular, very effective technique for imitation learning, which assumes a supervisor that can provide corrective labels to the agent after it's taken some steps in the environment. So Dagger will tell the agent what it should have done at those states. And then we can do supervised learning on top of that. So in our case, the supervisor is a corner pulling supervisor, which we can implement in simulation pretty easily. So it uses the simulator state of the fabric, iterates through the corner of the fabric, and figures out which one is the furthest from a target on the underlying plane. So here I've shown an example episode where there's 5 actions here overlaid with the arrow. The top row represents the color images, the bottom row represents the depth. And using both is very important, as we'll discuss. And from here, the coverage is indicated by the percentages below. So the supervisor starts at 38.4% coverage and then goes to 95.5 at the end. So that's how the supervisor works. We then transfer it to a physical robot. So we use domain randomization, which involves randomizing the color and camera parameters in simulation, so that the real world is just like another variation. We then tested on a Da Vinci surgical robot, and the motivation was, if we can get these policies to work on surgical robotics reliably, then this would enable applications like smoothing gauze or smoothing patient clothing. So for a physical experiment, we compared coverage using different input modalities. So we have the color, the depth, and the combination of the two. Those are fed into the neural network, which output the action. We then test all 3 of the modalities with the different difficulty tiers that we specified for this problem. And so what I want to highlight in the table with the blue boxes is that the input modality of using color and depth attain the highest final coverage, and they're the best on the harder starting configuration, where depth may be more pronounced due to a lot of extra folds and layers of the fabric. So here's an example of the policy in action, which was trained entirely in simulation. And we're in the upper left corner, we show the input that passed as input to the neural network. And we see that even though the corners aren't necessarily entirely exposed, it's still possible to do a pick and place action at roughly the correct region. And from here, the learn policy is able to get the coverage necessary to trigger a success criteria. All right, so that's the model-free deep imitation learning idea. Next, I want to discuss a very similar paper, but where we propose a different technique for fabric manipulation using model-based deep reinforcement learning. And I also want to acknowledge my collaborator, Ryan Hawk, who's another PhD student in our lab who worked on this with me. Okay, so from the last paper, we understood that we can get a fabric smoothing policy, but there's two glaring red flags. One is that we trained a smoothing specialist, so we're going to have to retrain for other tasks. Number two, we had to implement an algorithmic supervisor, and it was a little bit straightforward for smoothing, but it might be more complicated for other objectives. So the motivating question here is, can we have a more general fabric manipulation policy for an arbitrary goal image which specifies the configuration that we want the fabric to look like? So as part of this, we propose visual spatial foresight, which is a method that uses a video prediction model trained on simulated data without any task-specific demonstration, and then we can use that for planning. So if you're familiar with the framework of visual foresight proposed by our Berkeley colleague, it's fairly similar, except we're also adding the Dept component, adding the simulation data, and doing it on high precision tasks. Okay, so the first part of this is the dynamics model. In our case, the dynamics model is the same thing as a video prediction model. So the objective here is, given our current observation and a candidate action sequence, we want the prediction model to generate a predicted observation sequence of images. And what I want to highlight here in this equation is that this equation is a generative model that shows how do we sample the predicted images and what are we conditioning on. So this is based on stochastic variational video prediction. It's a very widely used, effective video prediction model. So we're conditioning on a candidate action sequence and the context observation, and then we're drawing from this distribution. One key thing I want to highlight here is that this distribution has a latent variable or a series of latent variables for each time step. And that's important because each draw of a latent variable will generate different plausible futures. And the reason why this is helpful to have the stochasticity in the model is that given our ground truth images, they might not convey enough information to characterize physics parameters of the scene. So that's where the extra latent variable comes into handy. So here's an example of the dynamics model in action. So here we have some color images on the left, the depth images on the right, and they're from the same image, except I just separated the modalities. So the top row represents the ground truth images. The image in the blue boxes are the context image. So those are the images that we would pass as input to the video prediction model. We then have 5 ground truth images after the context image, but these are the images taken from the data generating policy that we used, which was effectively a random policy. So we didn't want any task-specific demonstration. So the bottom 2 rows represent the prediction of our trained video prediction model, where they only taken the context image plus the 4-dimensional actions that are implied by the ground truth images. And from here, we see that even though the model, as they predict further in the future, the predictions get blurrier, which we would expect, the prediction might be sufficiently accurate for planning. So in this example, they're correctly predicting that the actions are leading the fabric to be adjusted so that they're in the upper region of the workspace. So from these promising results, what we can then use is this as part of a planner. And that brings us to the second major part of visual spatial foresight. So here we have a planner. So the planner consists of the combination of the cross-entropy method and model predictive control. So to quickly recap, though, the cross-entropy method is a derivative-free way of trying to optimize some objective. So here we're characterizing the distribution from a multivariate Gaussian distribution, which we sample action sequences. And each iteration of CEM will generate a sequence of action, compute the cost for each sequence, refit the Gaussian distribution to the top few of the sequences, and then repeat the process. And here the cost function is Euclidean distance to the goal image. So what we're doing here, and as shown in the image here, the leftmost column represents the current context image. The cross-entropy method will generate 5 actions, since that's the time horizon we set. At the very last time step, we'll compare the image, the predicted image, to the ground truth goal image, and then that's the cost function. And then from there, we use model predictive control, which will take the first action in the sequence of the best action sequence, and then we'll throw away the other action, and then redo the whole process. Okay, so that's the planner. So let's see the policy in action. So the goal image is shown to the left. That's what's passed in for the cost function. And then we have the rollout shown on the right. And we see that even though the policy wasn't trained on smoothing specific data, it's still able to do a reasonably good job here. But for the next result, the goal is to get the fabric to fold in an upper left triangular fold. And once again, it's able to do a reasonably good job in 2 action. Finally, the most interesting case here is with this double fold. So notice here how the double fold in the goal image has the corner in the lower left above the corner in the upper right corner of the fabric. And that's the same thing that we see in the rollout. And this may be one of the cases when the Dept modality is very helpful, since it may help to disambiguate the height of different portions of the fabric. Okay, so to recap, the VSF, the benefits are that the smoothing results are very similar to those of the imitation learning results that I presented in the prior paper, even though VSF isn't specialized to this task and can still do folding. But since we presented this paper, we had an issue with compounding approximation errors when we tried to get folding to work on a physical robot. So over the last few months, we wrote an extended version of this paper where we look at every step of the VSF pipeline. So the dynamics model, the cost function, and other things. And then we try to improve all the steps in the pipeline. And maybe this should have been obvious in retrospect, but the number one thing that helped to get folding results to work in the physical robot was improving the way that we generated the data set for training the dynamics model. So with an updated data set where we increase the length of the action magnitude. So originally we didn't do this because if you increase the length of a pole, that might make it harder for the video prediction model to predict the future because of greater pixel changes. But with an updated video prediction model, we found that this was sufficient for generating longer pole vectors in the physical robot, where here it took 2 actions to get the fabric into a folded configuration like in simulation. And the action magnitudes are limited, so it doesn't have the ability to pull across the entire workspace at once. Okay, so that concludes the model-free imitation learning and the model-based reinforcement learning perspective on deformable manipulation. So in this next paper, I want to discuss a slightly different perspective that uses a different architecture that might be well suited for manipulating deformable. All right, so for this new work, the main contributions are as follows. So we have a suite of 12 simulated tasks using PyBullet that span not only fabric, but also the 1D deformable like cable and the 3D version of bag. And all this is in an open source simulator. It's open source right now, so we encourage researchers to try their own algorithms on it. So we'll discuss the details of this later. The other main contribution I want to highlight is that we have some model architecture, some novel architecture that might be well suited for manipulating deformable toward desired goal configuration. So this is very similar to the prior paper where we have a separate goal image that characterizes what we want to rearrange the objects toward. So again, we'll go through the details of this later in a few slides. Okay, so with our benchmark, we have tasks that have cable, which are the 1D deformable. So all the tasks that we have, they consist of, within the PyBullet simulator, a single UR5 robot arm with a single suction cup gripper that has a workspace in front of it. And we can characterize the objective of a task using several ways. So one way is to specify it with a target, like some anchor target on the workspace, which in some examples here are the green lines or the green markers that we want the cable to reach. Other, like in the VSF work, are goal conditions. So for example, with the images above, the goal configuration shows where we want the cable to reach. And then we pass in the top-down image into our model, and then we want the robot to configure the cable towards that configuration. So other tasks involve fabrics like the one that I presented in the prior papers, except we're using the PyBullet simulator now. So one of the tasks involves wrapping an object. So we have to put an item on some fabric and then cover it. The other two involve smoothing toward a desired goal, even which might be characterized with some target anchored or a separate goal image. And what I also want to highlight here is that unlike in the prior two papers, the workspace is much larger than the actual fabric. So that might increase the task difficulty. All right, now finally, the most interesting case here will be the one with bags. So manipulating bags has a very obvious practical usage in that it helps us to transport many items simultaneously. But what we found was that the robotics community hasn't spent much focus on manipulating bags, perhaps due to the complexity in simulation and even manipulation with a physical bag. What we did here was we took a sphere and then we imported it into PyBullet. We removed some vertices near the top, which created a gap, an opening. And then at that gap, we then put in some rigid bead around the top to help stabilize the physics. So the bag task involved opening the bag, potentially inserting one or two items in it, and then maybe moving it towards a target zone. And other bag tasks, like the ones shown here, are also goal conditioned, where the goal image shows which items should contain the bag. Okay, so that's an overview of how our simulator looks like. We next move on to the other major part of the work, which is on an architecture for manipulation or rearrangement. So our architecture is based on something known as transporter networks that was presented recently at Coral last year. So to quickly recap from prior work, with transporter network, there are two major steps involved. So imagine we have this example here with a simulated UR5 robot arm, which had to move the rigid L-shaped block towards some target receptacle. The first step is to localize this region of interest. So that might be the picking point. So we're still dealing with the picking and placing paradigm. So the first step is to localize that region of interest. The next step is to infer the spatial displacement, or where this region should be rearranged to. And I also want to highlight a few things. The localized region of interest may encompass the entire object, part of the object, or multiple objects. Transporter network does not predict two continuous values that characterize the displacement. That might be very brittle. What it does instead is it infers it through a brute force search of deep features by overlaying it over all possible regions in the image. This creates a correlation map where the pixel that has the highest value is the placing point. So while this might sound expensive, if you think about it, it's really just a convolution where the localized region of interest is a kernel. And so this can be efficiently implemented on the GPU. So this is, again, a broader view of how transporter networks work. So what I want to highlight here are that the actual overlaying process relies on features computed that are the output of fully convolutional neural network, or ResNet-43, which produce both deep feature and also the crop that we then use for kernel in the convolution operator. Okay, so that's all prior work. In this current work, we want to extend transporter network so that it can take in a separate goal image, like in the BSF work, where the goal image specifies where we want to rearrange the object toward. So here's an overview of the architecture where we adapted it towards the bag task. So let's go through the computation of this carefully. As before, we have a current image which specifies the configuration. It then goes through 3 networks. So all these networks are fully convolutional networks that produce deep feature or logic. So all of this is pretty similar to the vanilla transporter network. What's different here is this extra goal image that we're passing as input to specify which bag should have the item. This goal image is passed through not only the picking network as well, but also a separate network that characterizes the goal feature. So at this point, we pass the input through 4 networks to get 4 intermediate features of the same dimensionality as the input. If this were a normal transporter network, we would then take a crop from the query network and then do a convolution over the key feature. But that wouldn't take into account the information contained in the goal image. What we do instead is, before we do the convolution, we have to incorporate the goal information, and we do that by using element-wide multiplication to get features that include the goal information. So after this, we're then at the point when we have what we call a query feature along with some key features. We then follow the convolution operator where we first localize the region from the picking point, and then we do a convolution over the feature from the key network. And that produces some features in what we call a placing heat map, where the highest pixel score indicates the placing spot. So what I also want to highlight here is that both the picking point and the placing point are just 2D numbers that represent the coordinate of which pixel consists of the picking and the placing point. And all this can be learned end-to-end through backpropagation from demonstration, where the loss function is based on the cross entropy loss, where each class is a pixel in the images. So that's the overview of this novel architecture. So let's see some examples in action of both this and the vanilla transporter networks on Deformable. So here's an example of this learn policy in action where it's on a 2-item bag task. So after opening the bag, it has to insert 2 items in there. And hopefully once that's done, it can then pull or pick at the bag opening. And hopefully that encloses the item in there, and then it can deposit it towards the target. So that's a success. We also have the goal condition version where the learn policy here sees that the target bag is already open, so it doesn't have to do any opening action. It will then pick at the item and then insert it into the correct bag. So we have results in the paper across all 12 of the tasks in the benchmark for the vanilla transporter network or the goal condition version, depending on the task. We compare those with methods that use ground truth, vertex, and pose information, and we find that transporter networks are orders of magnitude more sample efficient. So for more detail, we refer you to the paper. But a method did not come without limitation. And this limitation is common across all the 3 papers that I presented today, where if we put in a block here, but it's not properly enclosed within the bag opening, we see that the block can fall out. And this is an obvious failure case of the coarse kind of pick and place action that we do, which motivates policies that can try to recover from these failures in real time. Okay, so that concludes the discussion of 3 different research papers. In the upcoming slides, I want to first recap what we've learned and pitch some future work ideas. Okay, so to recap, we've shown some promising results for training pick and place action policies for deformable manipulation, which includes techniques like model-free learning, model-based learning, and transporter networks, which are also called action-centric because the process of doing a convolution operator will effectively test all possible actions in a brute force search fashion. We then show some physical experiments using fabric smoothing and folding, as well as simulated 1D, 2D, and 3D manipulation. So some limitations of prior work are, for example, as mentioned before, the whole notion of pick and place action can be limiting. And there's always room to improve for sample efficiency and generalization. So it's always very common with learning-based techniques to see that the learn policies simply do not generalize if you pick something out of distribution from the training data. So here's a flavor of some ongoing work which I've been advising on and which we also address different areas with deformable manipulation. So one ongoing work is the idea of using correspondence from simulation. So in this paper, which we'll be presenting at ICRA later this year, the main idea is to use simulated data to figure out correspondence. And so if we do some t-shirt folding task, for example, we might have a pick and place action that does a fold. And if the key is that if we see a different image of a different t-shirt, but it's roughly the same class, we should be able to figure out how to translate the fold from one t-shirt to another. The other major prior work that I've been advising on, which we'll also present at ICRA later this year, is with dynamic cable manipulation. So here we're finally moving away from the pick and place action paradigm, and instead the robot action are parabolic motion, which characterize a parabola, and where we learn the apex point or the top of the parabola. And we can get some really cool vaulting, notching, and weaving tasks. And for more detail, my advisor, Ken Goldberg, is giving a talk on this very topic at Toronto in a few hours. All right, so here's some future work ideas, and collaboration is welcome. So I'm always looking for possibilities to collaborate. So here's some ideas to pitch. So one is we should probably go back and investigate bimanual manipulation. So use learning for bimanual manipulation just because that gives us more flexibility in manipulation. We can also incorporate different sensing modalities like incorporating touch because especially when we're stuffing items into containers or other obstacles, like maybe in a suitcase, or back in the day when we traveled, we can use touch information in addition to vision information when we're trying to stuff items and when we can't fully see the object. We can also test and develop newer simulators such as Flex, and kind of related to an earlier point, I also think that we should develop some occlusion-aware policies that are aware of, of occlusion and can try to work around these issues. Okay, so these are some ideas, but the overall broader interest that drives my research here is, can we get robots to competently manipulate novel and challenging objects in unstructured settings? That's a grand challenge of robotics. I'm very honored to be part of this field. I'm very humbled to be considering this problem. I know that we have a long way to go, but I'm very excited to see what we as a community are able to accomplish in the coming years. So with that, I think I'd like to conclude the talk. So happy to answer any question now or by email. Here are some of my outstanding colleagues I'm fortunate to work with. And yeah, thank you for your time and attention. So yeah, that's it for now.
Yeah, thanks for the talk. It was really interesting. I just I guess I'll ask the audience, are there any questions now that we're finished?
So I have a question if nobody else has.
Sure, go ahead.
Hi Daniel, thanks for the excellent talk. I was wondering about two things mostly. The first one is about goal specification with deformable objects. So it seems like showing an image of the final configuration of the desired configuration is quite popular, but I'm wondering if there are any other alternatives to make goal specification a bit easier with deformable objects. How can you, for example, sketch the type of final configuration you want without providing an image of it?
That's a very good question. That's a very good question. And yeah, two things that come to mind are, number one, we can get sketches of the goal image. So here the challenge would be, how do we do, for example, if we're doing a model-based approach like I was doing in the second major paper, how do we relate the real image with the sketch? So like figuring out how they correspond with each other. Another thing that we could do is use intermediate sub-goal. So rather than just the final image, let's see if we can come up with some intermediate sub-goal, which might be easier to accomplish and maybe might avoid the agent going astray. But the downside of that is it required having those sub-goals in the first place. So a lot of times it's easier just to specify the final goal. So if we have some demonstrator that can give us an overview of how that trajectory should look like over time, then yeah, we should use that information, not just the final image. But I do think it's a very good idea of using sketches instead of just like maybe a high resolution image that might be very difficult to model or produce from an image video prediction model.
Yeah, I think in addition to sketches, I'm wondering if you thought about also specifications that concern the topology of the desired configuration. So for example, with the rope manipulation stuff, where you had also obstacles, you could think about the homotopy classes that are as a final specification. With the folding of the cloth, you could think about the types of folds you want to encode at the end without giving it a target, a desired location or a desired ordering for the folds. So I'm wondering, are you also thinking about topological ways to specify goals at the end?
Yeah, we haven't thought too much about that, but we should probably consider that. I think different ways of, specifying the class would be a good idea. Now I'm trying to think about how we might train that. So if we can figure out some technique that is able to relate the configuration of the formable with an underlying topological representation of it, then maybe we can use that information to specify a goal image, or maybe sub goal images. That's a very good point. I think we'll consider that for some follow-up work.
Cool. Thank you.
Yeah, thank you.
Anyone else have any questions? If not, then I guess like there's some meetings happening after
So
this. Oh,
I have one
oh
more.
yeah. Oh yeah. Florian, go ahead. Go ahead. Go ahead.
Sure. So Daniel, you mentioned Flex, for example, and other types of libraries like it, which are starting to become fully differentiable. So I'm wondering whether you think, or how do you think having access to a fully differentiable simulator is going to help you with your planning or your control here?
Yeah, I think that might help. I just have to check to see, is it going to be, how well does it accurately model the physics of real fabric? And obviously this also depends on which fabric we're using. So I have observed that, for example, Flex seems to be a very accurate or very promising simulator, but all simulators that I've tried, I've tried about, I think, 5 or 6 different simulators. I don't know if I've tried a differentiable simulator, but I guess another way of thinking about it is if we can get a simulator and then get some real data and then use the real data to tune the physics of the simulator. So if a simulator supports that kind of, change, I think that might be very promising as well, where maybe use a small amount of real data and figure out how to use that data to adjust some parameters in a simulator. I'm not sure if a differentiable simulator does that. Does it do that?
Yeah. So I think I can send you a link later on about something that you might find interesting.
Yeah. I think I would be interested. Yeah.
Any more questions from the audience? Seems like, yeah, I guess thanks for the presentation, Daniel. It was really interesting. I know there's definitely some people using like getting inspiration.
So
I think
such.
there's a connection issue
I
here.
think that there's one-on-one.
So Arthur, I think we're losing your connection. We cannot hear you.
Yes. Am I audible now?
Yeah, better.
Yeah. Okay. Yeah. So there was some signups on a sheet. So I'll send that link via email, and then if you and the interpreters are able to join that one, then yeah, that should work.
Perfect.